Simplifying trig expressions. So we want to simplify these expressions as much as we can. We want to get it down as short and sweet as possible. These can be tricky problems because there are often multiple ways of arriving at the correct final answer. The key is just to practice the different techniques until you really get them down. When I look at this first example, what stands out to me the most is that sine of negative theta, because I instantly think, gee, that's kind of complicated, but I don't ever have to leave that because of those negative angle identities. We learned that sine of negative theta is equal to the negative of sine theta. So I'm going to replace that. Instead of writing plus sine negative theta, I have minus sine theta. So that's already a little bit nicer. I'm looking for ideas of what to do next. One thing often worth trying is switching everybody over to sine and cosine. So let's do that and see if that helps us. Of course, here cosecant is 1 over sine and secant is 1 over cosine. I don't really want to write that as two separate pieces, though. I think that's complicated. I want to write it as one single fraction, 1 over sine theta cosine theta. After you do this for a while, you realize that if you have an expression that only contains multiplication or division of the pieces, you can always reciprocate the individual functions between the top and bottom of the fraction. So in other words, here I just had two pieces being multiplied. If I want to move cosecant to the bottom, I can do so by simply making it a sine. If I want to move secant to the bottom, I do so by making it a cosine. I could reverse that as well, right? I could take sine and move it back to the top, which is where it was, as a cosecant and so forth. So that often becomes a useful technique. Let's see, let's put that into practice for the second one. I have sine theta times secant theta. Again, this is just multiply divide stuff in that second term. I don't really want to mess with the sine theta. I'm trying to get everybody with sine and cosine, so I'll leave that on the top where it is now, but I will reciprocate the secant to the bottom, turning it into a cosine theta. Again, I could have done this in more steps by writing secant theta is 1 over cosine theta and then multiplying everybody across, but there really isn't any need when you're only dealing with multiplication and division. Now, so far you still may be thinking, are we really making this thing any better? And I know, it still looks like kind of a mess. What should we do now? Well, anytime I have two fractions being added or subtracted, I think, well, maybe I should go ahead and do the adding or subtracting and see if that helps me. You can only subtract fractions with a common denominator. This fraction has sine theta, cosine theta. This one only has cosine theta. So in order to fix it, I would have to multiply the top and bottom here by a sine theta. Now that each denominator matches, I can go ahead and do the subtraction. How do you subtract fractions? Well, the denominator stays the same. That's just sine theta, cosine theta. And then you subtract the numerators. So 1 minus, and then what is sine theta times sine theta? It is sine squared theta. Okay, this is where things get really good, because when I see a 1 and a sine squared theta in the same expression, it reminds me of the Pythagorean identity. Namely, sine squared theta plus cosine squared theta equals 1. I can manipulate the terms around here to form different expressions. In fact, I think you can see how I can form this one. All I would need to do is subtract the sine squared theta, moving it then to the other side. What that leaves me with then is cosine squared theta equals 1 minus sine squared theta. I would say you'll see the Pythagorean identity in this format probably just as often as you'll see it in the regular format. Going back to my problem then, when I see 1 minus sine squared theta, I know, oh, that's just the same thing as cosine squared theta. Notice how this problem keeps getting simpler and simpler. That's typically how it goes. I don't have any more adding and subtracting now in this problem, which means I can start thinking in terms of canceling. In other words, dividing out common factors. On the top, I have cosine squared theta. What does that mean? Cosine theta times another cosine theta. Well, great. Then I have a common factor of cosine theta on the bottom as well as one of those on the top. And all I have left now is a single cosine theta up top and a single sine theta at the bottom. Can I go any further? I can. Remember, the goal here is to get it as short and sweet as possible. Cosine over sine, that's a quotient identity. That's equal to cotangent theta. And so that original expression is equivalent to cotangent theta. We used identities and we used algebra. Those are basically your two tools. Let's look at the second example. This one looks kind of complicated. It's already a big fraction. Maybe you're thinking, oh, we should do some canceling here. Sine x plus 1 on the top, sine x plus 1 on the bottom. We cannot do that because the top is not a giant multiplication problem. The top is a giant addition problem with two terms. So thinking in terms of canceling, dividing out factors, that's inappropriate at this point. Maybe eventually we'll be able to do that once we get rid of all the adding and subtracting. So what will we do then? Well, often if there's an algebra step just crying out to be done, that's the thing to do. And when I look at this, what I see is a big FOIL problem. Do you remember FOIL from algebra, where you have a binomial times a binomial, and so you do first, outer, inner, last to multiply the pieces together? That's where I think I would start. So I have cosine squared x, and then I'm going to do my FOIL. So I have first sine x times sine x, which would be sine squared x. And then I have outer sine x times 1 would just be sine x plus inner another sine x. So 2 sine x's in all. And then the last 1 times 1 would be 1. So I've gone ahead and I've FOILed that out. Let me write my denominator down. Each step that I write should be equivalent to the previous step. Step by step, we're cleaning this thing up, making it a little bit nicer. Of course, this time the Pythagorean identity is even more obvious because here it is right at the front of this thing. Cosine squared x plus sine squared x, that is equal to 1. And so when I clean this up in my next step, the top is simply that 2 sine x term, and then 1 plus 1 is equal to 2. I have this 1 plus the 1 that I already had, giving me 2. The denominator is still sine x plus 1. So am I finished? Well, not quite. When you have a fraction as an answer, you have to check to see if it'll reduce. But you can't check that until everybody has been factored. In other words, until you are looking at multiplication problems. Notice on the top, there is a common factor of 2. I can factor that 2 out, leaving me with 2 times sine x plus 1. The top is now a giant multiplication problem. Yes, there's a plus, but it's tucked inside one of the factors. The denominator does not factor, which means it's its own factor. Sometimes I like to put a parenthesis around it to remind myself I tried to factor it. Well, do I have any common factors? Of course I do. I have a sine x plus 1 on the top. I have a sine x plus 1 on the bottom. Those two divide out. This problem simplified far more than you probably anticipated. It is equal to the number 2. Now you say, what does that mean? Well, it means back in the original expression, I don't care what angle you stick in for x. You can pick any angle you want. The answer to this expression every single time will come out to be 2. Okay, let's try another one. This one looks particularly messy. Again, the first thing that pops out to me are these negative angles. I know that I can get rid of those quickly. Don't be bothered by the squared here. Remember what this means. It means that the secant of negative x is all being squared. You can always write it that way if it helps you. Well, I'm going to use my negative angle identities. The secant function was an even function, and so secant of negative x was just equal to secant x, which means this part is simply secant squared x. Cotangent, on the other hand, was an odd function, and so the identity was cotangent of negative x equals negative cotangent x. Okay, so we've gotten rid of those negative angles. Where do we go next? I already have a single fraction. I could think about switching to sine and cosine, but I don't have any sines or cosines now. That might be a big mess. Here's an algebra thing that I noticed that I could do. On the top, there are two terms separated by the minus sign. What I'm noticing is that each of the two terms has a common factor of tangent x. I think I'm going to try factoring that tangent x out and seeing if that gets me anywhere. So that gets me tangent x on the outside. There used to be 3 of them sitting here, so now there will just be 2 tangent squared x, and I won't have any in this part, just secant squared x. Again, I haven't touched the denominator in this step. Well, once again, something is supposed to pop out at you now. This is a really good situation because when I see tangent squared and when I see secant squared, I'm supposed to think of an identity, namely one of those Pythagorean identities again. The identity is tangent squared x plus 1 equals secant squared x. So I'm looking at that. I'm looking at what I have. I'm trying to replace tangent squared minus secant squared. It looks to me that if I just moved the secant squared to the left and then moved the 1 to the right, I'll have what I'm looking for. So again, subtract secant squared x over here, subtract 1 over to here, and let's write down what we'll have then. The secant squared x will have a minus because I subtracted it to the left. And over here I have a negative 1 because again I subtracted that 1 over to the right. Well look, from that identity, tangent squared x minus secant squared x is equal to negative 1. This parentheses right here is equal to negative 1. So in my next step, I now have tangent x times negative 1, which would be negative tangent x, over negative cotangent x. Obviously, the negatives plus out. A negative divided by a negative is a positive. Where do I go now? I have no adding or subtracting. I have only multiplication or division. That means any of these individual trig functions can reciprocate across the fraction bar and become its reciprocal function. So let's get rid of the fraction. I can do that by keeping the tangent x on top, but then reciprocating the cotangent x from the bottom to the top, which will make it a tangent x. Since cotangent was the only thing down there, I don't even have a denominator anymore. And then all I have left is tangent x times tangent x, which is tangent squared x. We have simplified the expression. Okay, let's look at one more. In this last example, there are definitely several ways you could start. Maybe one thing occurring to you is switching everything to sine and cosine. I think that would actually work out pretty well. I think though what I see is that it would be very easy to add these fractions together right now by getting a common denominator. The first fraction has sine cubed theta. So if I adjusted the second fraction by multiplying a couple more sine thetas, right? It already had 1. I'll multiply a couple more. Then each denominator is now sine cubed theta. And because that's the case, I'm going to be able to add these two fractions together. Okay, so my second fraction is now cotangent squared theta sine squared theta over sine cubed theta. The denominators match, so let's go ahead and add. Our numerator will be negative 1 plus cotangent squared theta sine squared theta. And our denominator, of course, is sine cubed theta. Now that I have that, I think it would be a good idea to switch over to sine and cosine. In fact, this is going to work out really, really nice. Cotangent theta is equal to cosine over sine because of the quotient identity. Now I do have the squared, so this will be cosine squared theta over sine squared theta. And then, of course, I have that times sine squared theta. And don't forget the denominator. The denominator is just sine cubed theta. But then the numerator works out quite nicely because the sine squared thetas here cancel out. And so I now have negative 1 plus cosine squared theta over sine cubed theta. Once again, I'm seeing a 1 with a cosine squared theta, so I immediately start thinking maybe I can manipulate the Pythagorean identity. Okay, so here's the Pythagorean identity that applies this time. I'm looking to see if I can create a -1 plus cosine squared theta. Well, this works very similar to the last one. If I move the 1 over to this side, it will become a -1. And I'll have -1 plus cosine squared theta as long as I also subtract the sine squared theta to the other side. And so then I have -1 from subtracting the 1 plus cosine squared theta equals negative sine squared theta from subtracting that term. Be careful with all the positives and negatives. Going back to my problem then, we've learned that -1 plus cosine squared theta is the same thing as negative sine squared theta. And now we're home free. We don't even have any adding or subtracting anymore. We only have multiplying with the exponents. I have 2 sine thetas on top and 3 on the bottom, so I can cancel out both of the ones on the top, leaving me, of course, with a 1. I'm dividing each one out. And 2 of the ones on the bottom end up going away, leaving me with -1 over sine theta. But wait, -1 over sine theta, that's just going to simplify and be cosecant theta, negative cosecant theta. Here then is as good as I can make it, as short and simple as I can make it. We have simplified the expression. Thanks for watching.